Okay. So one last example for stick diagrams. For this logic, how can you convert into the AOI logic and layout by using stick diagram? Right. Yes, since you have a bar on top, right? Start doing this. AB is the AND logic. So for the PMOS, they should be in parallel, right? AB. Oh, so what I did over here is, you can do it either way. You can directly have 3 components in series on the top of the PMOS. That looks like too many series, too long for the structure on the top. So, but you can see there are common terms for these ones, so you can combine them together to make it look simpler, can be simplified. It's AB or A or B and C. I just combine these two in here, in this. And then you can start drawing the PMOS and NMOSes. Right? AB is 2 PMOSes in parallel on the top. So I did this first, but you can do this first and then do this, doesn't matter. So you can put this on the top or bottom for the PMOSes. What about this one? A or B. So A and B should be in series. And C, that's the AND logic. So for the PMOS, it should be in parallel with A or B. And A and B, they should be in parallel. So we're done with the PMOS. NMOSes, AB, AND logic in series. A, B in parallel, and C in series, right? So you want to draw this and then this. So these two should be A and B, and this is C. So that's the AOI logic for this circuit. We have been doing this for so long, and I mean, if you want to verify the logic, you can list all the numbers in the truth table and verify it. Let's try a few values and see if that's correct, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1. If you put 0, 0, 0 in this logic expression, so F, right? It's F, not Y. What is F? All zeros. It's going to be 0. Bar will be 1, right? And 0, 0, 1, 0, 0, 0, 0, 1. Zero, 1, 0. 0, 1, 0. 1. 0, 1, 1. 0, 1, 1, 0. 1, 0, 0. 0, 1, 0, 1. 1, 0, 1. 0, 1, 1, 0. 1, 1, 0. 1. This will be 0 because C is 0, 0 and something is 0. And this is 1 bar 0. 1, 1, 1. All ones 0. Let's verify some of them. If I verify everything, we're done today. So I don't want to take too much time on this. If we have 0, 0, 0, let's see if this is 1. So that's F. Right. All zeros for ABCs. Definitely, right? Since all zeros, all the PMOSes are on. You can definitely find a way to pull it up to the VDD. Verified. 0, 0, 1. Let's see if we can pull it down to the ground. 0, 0, they are off. This branch is off. 0, 0, off. So no way. 0, 0, 1. 0, 0, 0. Right? Here's a pathway to pull it up. Verified. 0, 1, 0. 0, 1. Off. 0, 1, 0. Off. No way to pull it down. 0, 0. Done. See? 0, 1, 0, right? So A and C are zeros. A and C are zeros. So this is a path to go to the VDD. 0, 1, 1. 0, 1, 0. This. 0, this is off. 0, 1, wait. 0, 1, 1. No. Wait. 0, 1, 1. 0, 1, off. 0, 1, 1. No, 1, 0. So off. So there's no way to pull it down, to pull it up to VDD. But for 0, 1, 1 here, for the NMOSes, 0, 1, 1, this channel is on. It's going to VDD. So tell me about this one. I'm going to let you to do this right now. 1, 0, 0, which way? And what are the transistors are being turned on to pull it up to 1? 1, 0, 0, right? So you have B and C are zeros. B and C are zeros. So these two are on. So it's going to VDD. But for the NMOSes, 1, 0, 0, 1, 0, off. 1, 0, 0, off, off. Verified. Just keep doing this, you can verify it real quickly. So we know this is working, right? Just memorize this kind of rule, the procedure, how to do it. Just do it every time in the future. So we know it's going to work. If you don't believe it, just verify it every time, which is fine. Since you guys are young, doesn't matter if you wasted for a couple hours to do this. I'm old, I don't want to do that anymore. I'm 35 years already. So we're done for this part. Let's do the layout. Layout. And 2 rails. And then what? A, B, C, 5 transistors, which was 6. 6 here. 1, 2, 3, 4, 5. I'll put it here. How do we figure out this structure in the layout? 2 in series, 1 in parallel. So if I draw a line from VD, introduce a signal to this transistor, to this P+, and I'm going to have these 2 in series, and on the right hand side I have another one in parallel with these 2 series PMOSes, right? So it's definitely implementing this structure. So 2 in series, 1 in parallel with these 2 series PMOSes. 2 in series, 1 in parallel with these 2 in series, but they merged to 1 point, so that's why you need to short these 2 terminals together with which layer? Metal 1. I'm done with this part. Next, after this, you want to have 2 PMOSes in parallel from this trace. But what I have is this. How can I make a parallel PMOS structure using whatever I have, starting from this node? Because this node is this node. And I need these 2 PMOSes in parallel. How can I do that? How? Anyone can just let me know. Think about it a little bit. I don't want to just directly give you a solution. Let's just think. Connect to where? Let me know. So all the metals, whenever you cannot imagine how to do it in your mind directly, you just try it, right? Just try a few options. And you do not have so many options here. Since all the metals are supposed to be connected metals, right? Or P plus terminals. These terminals have vias. You don't want to connect this to the gates. It's not what you're supposed to do. So there are only 2 terminals, right? You have to make some connection from here. And there are just 2 terminals available. Just try one by one. And if you try here, then it's shorting these 2 P pluses for this PMOS. It definitely won't work. So what you want to do is actually short it to here. That's the only way you can make this connection. And you're not really sure, actually, you cannot 100% make it work for every structure. You just have to try it. If it's not working, then you probably want to break it up in the middle and have 2 structures. Do not have all of them being shorted in one line, which is great because it's saving a lot of space. But not every time you can do it. I think 80% of the time you can do it, but sometimes you cannot. So for this time, luckily we can do it. So what I'm going to do, I will just make the connection from the top. Connect to here. So it's like from this node, right? This node, it's connecting this to this the sources of these 2 PMOSes, and so the current is going to flow to here and to here because this is one node. So these 2 PMOSes are in parallel, right? Is that correct? They're in parallel, and so the current will be merged to here, this point, which is this point, which is the output of this complex logic. So the output is ready. So I want to draw the NMOSes. One, two, three, four, five. Again, if you cannot imagine a instant answer or solution for this, just try a few times. Then we'll be able to find it. So what I did here is I connect to this point and this point. So for this node, if I connect to this point, I'm getting 2 parallel NMOSes, which are these 2 guys, right? Parallel NMOSes and merged to this point. And then I need a series NMOS after this point. So what I did is I shorted to here. So merged here and go through this NMOS, go through this NMOS, and this one should go to where? This node. Ground, right? So you want to be careful about it because they are both metal ones, and you probably have to, find a way to get around this line. You can go up and go down, but anyway, since there will be a lot of traces in the middle, so you have to find out the vias get into metal 2 or even metal 3 to not shorting these circuits. I'm just drawing this for us to understand this easily. I don't have too many colors of markers. Spacing in where? Yeah. Yeah. Yes. Yeah. You can. Yeah. You can expand it a little bit. Yeah. If you need more space in the middle, you can definitely do that. But keep in mind, there's one tip here, because eventually you are going to build a functional block in electric VLSI. So at the very beginning, I draw an inverter because inverter is super simple. You don't need that much space in the middle. So I normally just draw a really tiny inverter like this, right? And after I have all these other structures designed, because I have to expand it to make more space in the middle to run the traces. And I want to place this inverter, along with all these structures to make one block. So I find out if I directly grab this inverter, I'm getting this, which is not ideal. And so I have to come back to expand the inverter, make it like really slim and tall like this, afterwards. Okay, which is fine. It's not really difficult. It's just you can there's a ruler tool in electric VLSI. You can measure this distance. You just find out the longest one of any of the blocks you have developed. Just measure the distance here, and then go back to the inverter's layout, expand it to exactly the same length, so you can just put it back here in the future to make a one functional block. So let's finish up this one. What's next? We have, so here's these two wires is this node, and connect to here, and in parallel, two NMOSes in parallel and merge to this joint and go over here, which is a CMOS. NMOS has a C signal being fed into the gate, and this should be grounded. This should be grounded, right? And then we haven't done this part yet. So let's come back to this node, because this is this node. And directly after that, you should have two NMOSes in series. Anything else we need to do? Layout to make it exactly what the schematic is doing. Anything else we need to do? Right? Done. We don't have to make any more connections. It's already in there. All right. That's for this one. You are going to have a lot of examples in your homework 3 assignment. Just practice with them. And if you cannot directly make it work just using one string like this, you just want to break it up in the middle, which is fine. So you just don't want to do like, if I can do it in one string and you break it up in 5 strings, I'm going to take points off. If you only break it up in the middle for once, which is it's fine. I mean, but I'm going to give you a solution to improve it in the future. But just don't want to do too many of these ones. You want to design it, think about it, how to design it, and make it compact. We have some examples for designing an adder. So you guys know that the structure for the regular ripple carrier adder adder. S is CO is 1 bit. Still remember what are these? Nope. A XOR B XOR C. CO, A or B, CI or AB. So definitely you can design a gate level circuit, logic circuit to implement this logic, like what we have done a lot of times. A or B, and a CI or AB. This S is CO. It's a lot of gates. And every single XOR gate has a lot of gates inside as well, if you do not use AOI logic. So this slider is actually huge. So if you have a lot of transistors inside, a lot of traces, the problem will be time delay because you have so many parasitic capacitors inside. There are traces, and because all the circuits are built in the silicon wafer, there will be a dielectric materials. All these gates has oxide in the middle, so they have capacitance. And it's going to increase the time delay for the signals. So this is actually really slow. It's a slow slider. It's not ideal design. So we want to improve it since we have learned AOI logic. So we can definitely implement it using this one. Whatever we can get from here, right, to make it easier and faster. But I think before we do the AOI logic, I want to show you some of the, trying to remind you, how to make a subtractor out of it. So is this a 1-bit slider or 3-bit slider? 1 bit. Why? It's just adding A and B. So a 3-bit slider looks like this. C minus 1, CO, C1, C2, A0, A1, A2, B0, B1, B2. So that's a 3-bit slider. And all these are the summations, S0, S1, S2. So the C2 is a MSB for the final result. SO, S0 is a LSB for the final result. And how can you make this into a subtractor? Convert it into a subtractor. 2's complement, right? How to do 2's complement? This is adding because the slider is adding all these numbers. Two's complement, what's the definition for that? You invert all the bits and add 1 to the result. So it's actually A minus B. You implement it by doing this. So we're going to use the same structure to do it. Okay. So the method 1, which you are going to do it, run the simulation schematic in electric VLSI for the homework 3. And I'm going to ask you to design this one and verify the logic. That's A2, A1, A0. That's B2. B1. B0. That's a control bit. You want to directly feed the control bit to the carry-in of the first FA. So that's the final result. How this works. What are these gates? These gates? XOR gates. Okay, so the B zeros. So B0, B1, B2 is the other addend to this adder. So you're adding A2, A1, A0 to B2, B1, B0, right? And the final result is C2, S2, S1, S0. That's what this structure is doing for you. And the control bit is just a digital logic, right? So it can only be 1 or 0. And if you are feeding a 1 to this control bit, so you are having all the B's XORed 1. So if 1 XOR B, what is the result? 1 XOR B. You have to think about what is B. If B is 0, let's see, if B is 0, what is this? 0 XOR 1, what is that? 1. Remember what's the function for XOR? If they're different, you got a 1. If they're same, you got a 0, right? So XOR is trying to detect the difference if they're different. So they are different. 1. They're the same. 0. So it is inverting B. Right? If I hide it, you can see if I have a 1 for the XOR, for the other input for the XOR gate, so actually this XOR gate is inverting B. So I'm 50% of the way to implement 2's complement, because I have to invert it first and then add a 1 to the result, right? To convert into its 2's complement. Still remember that? So if I have 1, 0, 1, 0, 0, 1, 0, 1, what is that? In 2's complement. What is this? In 2's complement. Come on. 5. So since this is exactly 5, it's defined by the nature, by the God, right? This is definitely 5. No one can argue for that. This is 5. Because we have a computer system that's a binary, and we want to use a sign to represent negative numbers, right? We couldn't do it if we do not design this 2's complement system. So that's the purpose, since we need a negative numbers, and you cannot do it without using a artificial, I don't want to say that, just human-defined method to represent it. So the way we define it is, if you want to find -5, we just flip every bit and add 1 to it. as one of the ways to do that. You can use 1's complement, which is only flipping all the bits, but not adding a 1, which we found a huge flaw of it. So we stopped using that 30, 50 years ago. But we just found out 2's complement is perfect. So all the computers now are using 2's complement. Clear? To make sure everybody is on the same page. So we need negative numbers. That's why we use 2's complement. So we flip it and add a 1 to it. So that's -5. Is this really -5? It is not. We define it. We just call it -5. Actually, it's not -5. If you just look at the numbers, this is just a binary number. It's not -5. What is this? 8 plus 3 is 11. Right? But we just force it to be -5 so we can represent negative numbers in the computer. Right? Is that making sense? Great. So now let's find out the negative numbers for B2, B1, B0. That's a 3-bit binary number. We just need to represent it in 2's complement. How to do it? Flip it at 1. By using the XOR gates, we have flip it. The flip, we have inverted every single bit by doing this, by giving a 1 to the control bit, which is the control bit is being fed into the other input of the XOR gates, right? So we can flip B, so we can get a B, the inverted version of B to here. And then we need to add 1 to it, so we directly short this pin to here, to the carrying of the first of the LSB. So we are adding 1 to it, to the result. So invert it and add 1 to it. So we can do it at the same time because we short this pin to here. So whenever we have a 1 for this control bit, it is actually doing a 2's complement for the B's. So we can directly convert B2, B1, B0 to its 2's complement. Okay, so this circuit is actually doing a subtraction. It's A2, A0, A1 minus B2, B1, B0. If we give a 1 to the control bit, that's a subtractor. Because it's doing A plus. You cannot change the full adder. The full adder is always adding these 2 pins, these 2 numbers. So it's actually doing A plus minus B, which is exactly A minus B. And if we give a 0 to it, so there are 2 possibilities for B. So we give a 0 to the control bit. Same 0, same 1. So these numbers are duplicating all the B's. It's not changing anything. So B will be directly transferred to this position and making all these additions with A's, right? So it's not changing anything. So that will be a adding function. If you give a 0 to the control bit, it's making, and you are not adding anything to the carry in, it's not changing the number. At the same time, it's directly transferring B's to this point. Just doing an adding function. So that's the subtractor you can use. Where resulting in 1? Here? Which one? Say it again. Here? Yeah. Yeah. No, 1. Oh, yeah, right. Control B is 0. Sorry. 1, right? They're different. Good point. Thanks. All right. Clear on this? And there's a different way to do the same circuit, implement the same logic. We can use multiplexers or mux, right? Mux. 2-to-1 mux. The circuit, let's do the circuit first. mux. That's a control bit. I put S here, but do not confuse it with all the S here. Different S. Yeah, I directly short it here. So mux, what a mux does for you. That's a selection bit. That's Y. So the logic for mux is if you have S to be 0, it's sending A0 to Y. If S is 1, it's sending A1 to Y. So it is actually S, A1, A0 for the truth table. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0. So when S is 0, it's copying A0 to Y. When S is 0, you just directly write down A0 to Y. 0, 1, 0, 1. So whatever A0 is, just duplicate to Y. When S is 1, it's sending A1 to Y. So here's A1, 0, 0, 1, 1. You want to design the circuit, you need to draw the key map. S, A1, A0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. 1 here, 0, 0, 1, 0, 0, 1. 1 here, 0, 1, 1, 0, 1, 1. 1, 1, 0, 1, 1, 0. 1, 1, 1, 1, 1, 1. Group. Oops. That's one hazard. So you want to group it to get rid of the hazard, but that's fine if you don't do it here. It's better, just do it, okay? So what's the logic expression for this guy? 1, 1, these two guys, S bar, which one is being toggled? A1, so you want to directly write down A0. For these two, S, and which one is toggled? A0, so directly write down A1. So that's the logic expression for this 2-to-1 mux. And since you have this, you can design the gate logic, the gate level logic circuit, implement this logic. No problem, easy. Draw the circuit, the gates in there. However, this is not ideal. If you do it according to the gate level circuits, it's taking a lot of space. You can imagine, right? So many gates in there. So I'm going to introduce the simplified version of the 2-to-1 mux on Monday. So we can use that one instead of using this one, which is not ideal. Or I'll see you on Monday. I don't think you're ready to do all the problem in homework 3. I think this is due next Friday. And on Monday, I'm going to introduce more about more examples so you can complete homework 3 after Monday's lecture. But you can start working on it right now for some of them.